Hello everyone, my name is Bin, a PhD student from Huazhong University of Science and Technology. It's my great honor to present our work DualFS. It's a file system about Flash with dual mode switching feature. This is our layout. We will first give some introductions. Flash controller and Flash arrays offer the significant performance improvement over HDD because of their inside parallelism. We can see from the overview of SSD, Flash arrays are divided into multiple channels, chips, dies, planes to respond to error requests by parallelism and pipelining. But some unpleasant characteristics of Flash have to be dealt with carefully, such as the auto-place update property. That is, the erase operation is at the block granularity, while the read and write is at the page granularity. So we need address mapping, garbage collection to management the flash memory. Certainly, flash manufacturers scale flash capacity by storing more bits in one cell. 1 bit per cell is called SLC, 2 bits per cell is MLC, 3 bits per cell, the TLC, and so on. But with the increase of more bits per cell, the cell performance decreased. You can see from the table. The program latency is much longer in TLC or MLC than it in SLC cell. Nowadays, a block has more pages. It calls the big block problem. On one hand, long write latency makes writing 12 pages cost more time than an erase operation. On the other hand, the big block calls more page migration during GC with a patently long delay. From the figure, with the increase of pages per block, in some benchmark here, the file server, a GC procedure may migrate more than 700 pages with a near 1 second delay. There is another problem with SSD. The file system and SSD work independently, which leads to semantic gaps. The host and the SSD device are both bluntly designed without knowing each other's schemes. As a result, both the host and the SSD manage their own address mapping, garbage collection, and other redundant works. I will show that a data grouping scheme in FS that is broken by the device FTO algorithm. Data in the logical groups are mapped randomly in physical blocks. Open channel SSD and the dual mode switching of Flash give a new chance for solving the above problem. OCSD explores the interface to the host so that FS and the device are no longer knowledge of each other. And the dual mode switching enable Flash blocks to switch between the high performance SLC blocks and the large capacity MLC or TLC block. So we get a simple idea. With the help of OCSD, we want to combine FS semantics to maximize the usage of SLC blocks to speed up the I/O requests. Now we come to our design. Here is the whole architecture. The FTO in our system is called LBLK. It only implements a segment mapping. All other management are achieved in FS. We first add SLC groups in FS, and then set the SLC admission rule with SLC write bucket to utilize the SLC area. The GC for both the SLC and MLC are united. The figure shows the structure of well-known F2FS file system. We have two main clusters, which are the node and the data. Both of them are further divided into 3 groups: hot, warm, and the cold. Each group has a corresponding active segment, so we just simply add 2 SLC groups to the data and the node clusters called the SLC data and the SLC node. Then we have to decide what kind of requests can be written to the SLC groups. We first use an equation to calculate the profit of one request based on its hotness and priority. The priority levels of different kinds of requests are listed below, and the hotness is got directly by the classification of original F2FS. Only when the profit is larger than a threshold, the request has chance to be written into the SLC area. Next, the request that passed the first profit filtering will have a secondary filtering. The general idea is that we only want to speed up critical requests, so we classify whether a request is critical by IOQ deep first. The busier the device is, in other words, a queue is filled with more requests, we will give the more chance for the request to be written into the SLC groups. Moreover, the read request needs to wait until the data is returned back from the device, while the write only has to submit a request. So, if there are more read requests in the queue, the request has more chance to be written into the SLC groups. We also consider remaining capacity of SLC area. In conclusion, the secondary filtering is based on multiple dimensions, and we get SLC write ratio lambda. Data will be written into SLC area at ratio lambda in a given window. We notice that writing SLC block will lead to more erase counts, because the size of SLC block is half of the MLC block. The maximum size a device can be written is the maximum erase count times the capacity of SSD. We first set a goal for the device. The SSD need to support at least writing WMIN data. Our idea is to limit the data writing into the SLC groups in a certain data window. The remaining write size that needs to be guaranteed is WMIN subtract the data that are already written. So the data written to MLC area plus data written to SLC area need to be greater than W. The data written to MLC can be calculated by beta times X times M, where M is the MLC block size and beta times X is the erase count that's consumed in the MLC area. Similarly is the data written to the SLC area. Finally, we solve the equation to get the maximum beta. So, every writing delta size data, SLC write bucket is got by this equation. Let's review the whole process. If the SLC write bucket has been reached, the data will be written to the original groups. Otherwise, it will enter the SLC admission rule, and the SLC admission rule is judged by the profit filtering and how busy the device is. Last is the global GC. We implement a united segment mapping to align FS management size and device section size. There is only one GC procedure for both SLC and MLC area, and also for both FS and device. Finally, let's go through the evaluation. We use FuMu as our test environment. FuMu is a QMU KVM-based virtual machine manager. Three kinds of benchmarks are used. They are FIO, FailBench, and PostMark. The comparison schemes are OCSC-based FS AMF and other dual-mode FTL. Here, DualFS no WB is a DualFS without write bucket, and the default write bucket of DualFS is set to 80%. All test parameters are listed. DualFS achieves higher throughput than all other schemes, and DualFS without write buckets gains more improvement. When it comes to random write and sequential write tests, DualFS gains stable improvements as time goes on. Due to the speed up of critical requests, DualFS also achieves lower read response time, and the right figure points out the dynamic adjustment about the SLC area. In this test, we changed the write bucket ratio from 80% to 95%. The write bucket schemes works well as the lifetime meets the standards we set for it. This is also write bucket results for different FS in terms of erase count. We can see that straighter write bucket has fewer erase count. In conclusion, DualFS successfully speed up the FS by dual mode switching with open channel SSD. Thanks for listening. This is all about it. If you have any question, please feel free to ask me.